So now let's start with the design and analysis of algorithms. This video will be in less depth than the previous to get more concepts across. First, the definition of an algorithm is a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. So algorithms are normally developed mathematically, then translated into a computer program. So be ready for programming in your lab and more math in lecture and on tests. So here's a simple one. If you wanted to make 93 cents using the minimum amount of pennies, nickels, dimes, and quarters, how would you do it? Well, you would probably start with the highest value coin and take as many as you can without going over. Then take the next highest coin and keep doing the same thing, add as much as you can, then again with nickels, and lastly with pennies. This is probably what most people do and is called a greedy algorithm. You start with the highest and just work your way down. This works very well and is an algorithm you can tell the computer to perform. It'll loop through all the types of coins from the biggest down and give you an answer. But what if instead of 25 cents, a quarter was worth 26 cents, and you had to make 30 cents? Using that same algorithm, you'd have the 26-cent coin, then 10 won't work, 5 won't work, so you just add 4 pennies, and you'd get 30 cents. But is that the minimum amount of coins? Not this time. The greedy algorithm isn't the best. The best would be 3 dimes in this case. So you'd have to do something else. You need to think of the mathematical steps to take that can get you to your answer as fast and efficiently as possible. The greedy algorithm probably made a lot of sense to you, but now it's not so obvious, and this is just a basic example. You'll analyze shortest path algorithms. We're given a bunch of paths. What is the shortest distance from one point to another? Here you can see how graph theory comes up again. You have to not only know the algorithm, but also prove it, as you will with most algorithms you learn. You also learn the knapsack problem. We're given boxes with money and weights. How do you put them in a knapsack such that you have the most amount of money while keeping the weight under a certain amount? You'd probably come across Euclid's algorithm, but you've already seen this in our last video. It's an efficient algorithm for finding factors of 2 numbers. Now you can spend an entire career working on algorithms. If you just do a search for algorithm developer jobs, you'll see what kinds of positions are out there, but note a lot of them are not entry-level jobs. Also, to really emphasize how math-based this is, math majors often have options of graduate level classes or elective classes where they learn about algorithms as well, so this is not just for computer scientists. Now moving on, you'll probably hear that computer scientists focus more on software, while computer engineers focus more on hardware. But computer scientists do encounter a couple hardware classes, but not many. So one example would be learning computer architecture, where you learn more about the hardware design of a CPU. This is what's going on deep inside a computer to make it work. You'll understand how instructions are actually carried out in a computer and how the data is moved through memory locations. If this kind of stuff seems interesting, then computer engineering may be better for you. And the last class I'm going to go over briefly is the theory of computation. This is where things get really weird. This is where you ask how efficiently problems can be solved with an algorithm and what is possible by a computer. To draw a parallel, if we go back to the ancient Greeks, they were concerned with what figures could be constructed with just a straight edge and a compass. With just those 2 things, you may have learned that you can make 2 lines that are perpendicular to each other. People have created multiple-sided polygons with them, and turns out you could construct a polygon with over 60,000 sides if you wanted. No one has, but all we care about is that you can prove that it can be done. This is what we're concerned about with computer science. So yes, there's more proofs to come. So I'll give you an example of what a computer can't do, which has been proven. A computer cannot detect an infinite loop. Remember when I talked about loops briefly and how you could write the numbers 1 through 1000 with just one loop? Well, if you don't write your code correctly, you may accidentally make it so that the loop never stops. It'll write the numbers 1 through 1000 and then just keep writing 1001, 1002, and never stop until you manually terminate the program. This is called an infinite loop, and the computer cannot tell that it's happening. It doesn't know that it will never end, and if it could, we could use that to our advantage. For example, there's an unsolved problem in math that says that every even integer greater than 2 is the sum of 2 prime numbers. So 4, 8, 42, 102, you can all make up with prime numbers. This has been proven up to 4 times 10 to the 18th. But no one has proven whether this is always true. It just seems like it is as of now. Well, could a computer solve this for us? If one could detect an infinite loop, then it would be easy. We'd write a program that looped through the even integers and check whether it is a sum of two primes. If they find one isn't true, then stop running the program. Otherwise, it would run forever, and if the computer could detect an infinite loop, we just have it say yes, there's an infinite loop, so all even numbers are the sum of two primes, there will be no exceptions. But this method won't work for this problem because computers don't know if there's an infinite loop. Now this class has way more to it and it's just too technical for a video like this, but know that the only prerequisite for this class is really discrete math. So again, you can see why I went into detail on that class in the last video. Now to summarize everything, computer science does involve a lot of programming in multiple programming languages. Then there's a lot of math, specifically discrete math, that is used in algorithm design and analysis, as well as theory of computation, both which will involve proofs of the problems at hand. Now hopefully you notice this math is not what you're used to. It's not finding when a particle is speeding up or slowing down based on its position function, or doing vector analysis, and it's not learning more integration techniques for those who have taken calculus. It's mostly discrete math and the math behind how computers perform tasks. You could see calculus in your computer science courses, but it comes up very rarely, especially compared to majors like physics or electrical and mechanical engineering. You'll also do some hardware programming, and there are many electives you can choose to go into. Now there's more classes that I didn't cover, like programming languages, or sometimes they see operating systems, and I didn't even scratch the surface for the topics I did cover. But hopefully this gave you a good overview of what you can expect. So if you want to just learn programming, then these three majors will teach you. And even a math or electrical engineering degree with a minor in computer science will also involve a good amount of programming. But if your career goal is to do something like create websites or apps, then computer science is a good route, but it's not the only one. You can learn how to program in other ways, like online or through boot camps or whatever. But for those who do choose computer science, just be ready for all the other topics that I covered and more. So if you guys like these videos where I show applications but also a little of what you can expect as you go through college, then don't forget to like and subscribe.